computing a flux integral of a vector field in 3 dimensions through a surface in 3 dimensions is one of the most, it can be one of the most nasty computations that we do in sort of introductory vector calculus. And so for that reason, we're not going to do a lot of direct computation today of flux integrals through pieces of surfaces. That's one reason. The other reason is that we have two different theorems which can help us to compute flux integrals without having to compute them directly. Right? We have, on the one hand, if my surface is a closed surface, we have the divergence theorem that can help us out. And on the other hand, if my vector field happens to be an exact vector field, then I can use the vector potential function and compute the circulation of the vector potential function instead. So we're going to have a couple of ways to avoid direct computation for flux integrals, but we'll do a couple of examples of how we would compute a flux integral directly using a parameterization for our surface, and that's going to be where we start today. Right, so this last day of our class, we're going to look at two different sections out of the text. And the first one is our section on flux integrals. The second one is the section that explicitly covers Stokes' theorem. So our first objective in the section on flux integrals is going to be to figure out how to think about the flux integral of a vector field through a surface. And the good news, I suppose, is that we have had some experience before this point parameterizing surfaces. And the great thing about being able to parameterize a surface is that that parameterization actually gives us traces. If we just set one of our parameters in our two-parameter parameterization for a surface equal to a constant, then what we get is a parameterized curve, which is a trace. It's sort of like a coordinate line, if you like, that lies along a surface. So if you imagine I had a parameterization of this surface we're seeing over here in the variables s and t, then if I set s equal to a constant, then I'm going to get a curve that depends only on t, and which is a trace on my surface. Similarly, if I set t equals to a constant, I'm going to get a parameterized curve that goes in the s direction, if you like. And so what's good about those is that each of those parameterized curves, if we take its derivative, is going to give us a tangent vector. So this red vector here is a tangent vector to this red trace, which is probably, s being the variable and t being a constant. Actually, no, I think this is probably the t is a variable, s is a constant, is that the red curve in the red direction. And then the yellow curve, it looks like it probably has the s direction being the variable and the t direction being a constant. And so once I have two independent, those of you taking linear algebra with me will recognize exactly the sense in which I'm using that word, because we just talked about it about not quite even 12 hours ago. If we have two independent tangent vectors, two independent directions, so if my grid lines, if you like, if my traces meet at anything other than a 0 or 180 degree angle on my surface, then they determine this little parallelogram. Right? When we talked about surface area, we were able to use that tiny little parallelogram as a way to compute the surface area of a parametrized surface. Right? But how we got it was that we found that that parallelogram's area was equal to the magnitude of the cross product of these two tangent vectors. And so the magnitude was interesting for us when we were finding a surface area on a surface, but now the direction is equally important for us. Because if my two vectors that I get by taking the derivatives of my parameterization with respect to each of the two parameters, s and t, if those give me tangent vectors, what am I going to get? What relationship is their cross product going to have to the surface? Because the cross product of two vectors in 3 dimensions is perpendicular to each of those vectors, the cross product of these two tangent vectors to my surface is going to be perpendicular to both of them, and therefore perpendicular to my surface. So I would call this green vector that we're seeing here a normal vector to our surface. It can also be thought of as a normal vector to the tangent plane to that surface, which is probably a better way to think concretely about where this thing comes from. So if I take the two partial derivatives of my parameterized surface function and I take their cross product, I get a normal vector to the surface. And we can use those normal vectors as a way to assess the extent to which a vector field is aligned with a normal direction to our surface and therefore has positive flux through my surface. Or if my vector field happens to be flowing along the surface instead of through it, then the dot product of that vector field with my normal vector ought to be 0. And so our flux would end up being 0. And of course, these things can vary from one point to another point on my surface as I sort of move around, right? And so when I say normal vector, we're not getting a single vector. We're getting potentially a different vector at different values of s and t as I move along my surface. So in our opening act for today, preview activity 12.8.1 is just going to ask us to parameterize some surfaces and then do this computation to figure out whether what we claim is happening here actually is happening, that we're getting the right normal vectors that we're supposed to get by taking derivatives of our parameterization. This preview activity would probably, if we just like sat down to do the whole thing, would probably take us the entire class. So rather than that, what I've done in your activity streams for today, this is in 12.8, is I have helped us out with parts A and B, or at least part A. I suppose the part B graphs are a part of the part E visualizations that I've also helped out with. So basically, the one part that I want you all to work on as part of today's introduction is part C. So let me quickly talk us through what happened in A and B. So in A, we're given these three different surfaces: a sphere centered at the origin that has a radius of 3, a right circular cylinder centered on the x-axis of radius 2, where x ranges between 0 and 3, and then the portion of the plane x plus 2y plus 3z equals 6, which resides in the first octant. So x, y, and z are all positive. So that piece of plane is actually going to be a triangle with its 3 vertices on the x, y, and z axes and residing in the first octant of x, y, z space. So I took the liberty of coming up with these parameterizations. And you might recognize that the way that I did it is I made use of our curvilinear coordinate systems. So for my sphere of radius 3 centered at the origin, I wrote out the spherical coordinate system, right, in terms of x and y, in terms of rather rho and theta and phi, right? X is rho sine phi cosine theta, y is rho sine phi sine theta, and z is rho cosine phi. And then I said, well, what do I know? I know that the value of rho, the radius, the distance of all of my points to the origin, is a constant on this sphere. So rho must be equal to 3. So replacing rho by 3 and then letting theta and phi become my parameters t and s respectively, I get a parameterization for the sphere of radius 3. It looks an awful lot like the parameterization that we discovered way back in the second week of our course when we were first introduced to the idea of parametrizing surfaces and spherical coordinates to begin with. Similarly, for cylindrical coordinates, the only difference here is that this cylinder is centered on the x-axis instead of on the z-axis, where our traditional cylindrical coordinates are centered on the z-axis, right? So all I had to do here was just sort of replace the role that was played by x with the role that's traditionally played by z in cylindrical coordinates, and vice versa. So I just traded places with my x's and my z's. And so this cylinder has a Cartesian equation, y squared plus z squared is equal to 4. Wait a minute, that means that I have a typo in my parameterization here, so let me fix that while I'm talking about it. And so the fact that x ranges from 0 to 3, this is sort of like the z in my cylindrical coordinates, that is just a coordinate unto itself. I don't have to do anything special for its parameterization. I can just let s mean the same thing as x does, just like it would have meant the same thing as z does in our traditional cylindrical coordinates. And so the fact that y squared plus z squared is equal to 4 means that y and z can satisfy y equals 2 cosine t, z equals 2 sine t. And so there is my cylindrical parameterization for this one. This piece of plane in the first octant is a little bit challenging. We can write the equation for this plane by solving for any of the variables in terms of the others. So to avoid fractions, I decided to solve for x. So x is 6 minus 2y minus 3z. And so as a parameterization, then I'm using y and z as my parameters. So y equals s, z equals t, and then x is 6 minus 2s minus 3t. But then I have to let y and z be constrained by residing within the triangle in the in the yz plane, which has vertices at the origin as well as at the largest value for y, and the largest value for y ends up being 3, so we solve for the y-intercept of this plane. And then the largest z value for this plane is going to be the z-intercept, which is 2. And then I have to parameterize where y and z range within that triangle. And so that's where I had to do a tape measurement here to get basically y ranging from 0 to 3 and z ranging from 0 to 2 minus 2/3 y. So it's just the ordinary sort of tape measuring that we would have done to get a tape measurement for that triangle. Okay, so there are the parameterizations. And so in part C, what you're being asked to do is to compute the curves, which are the trace lines defined by these parameterizations on our surface. And those are the derivatives of these parameterizations with respect to s and t, respectively. And then the cross product of those to find an equation for what we might call a normal vector field to our surface, because it's a bunch of normal vectors, one at each different point on the surface, which is defined by our different values of s and t. So let's take 15 minutes or so and work on getting this normal vector computation done, because we're going to need this later on today. So when we're finding the normal vector for this parametrized sphere, we take the s and t derivatives and end up with these expressions, and then we have to do the cross product of those two. And so you can imagine, right, why we don't do too many direct computation flux integrals, because it gets pretty nasty, but then in this case it gets a lot simpler as we get closer to the end of the simplification. But let's just do out the cross product and get it in all of its glory here. So the first term of my cross product is going to be this product minus this product. So this is, I can never, every time I do a cross product, I'm always like thinking in my mind, like making these little butterfly shapes to figure out how to multiply the right things together to give me the thing that I need. You could also use determinants or whatever, but this is just the way that I best seem to connect with it. So when I do that, I get 3 cosine s sine t times 0 minus negative 9 sine squared s cosine t. So I get 9 sine squared s cosine t, which is what you all had. Well, you had a minus, and I think that was just, did I end up with a...
No, I think what, oh, I see what I did wrong. I put a sine t for the first component and it was a cosine t. Okay.
Oh, okay. Yeah, even
Yeah.
just even one little slip like
Yeah.
that can rule out a whole lot of simplification that we're going to want to do. So if we forge ahead here, then it's this product. Oops, no. It's this product minus this product. I'm really cluttering up my diagram here. But so it's negative 3 sine s times negative 3 sine s sine t. So that's going to be negative 9 sine squared s sine t minus 3 cosine s cosine t times 0. So that one ends up being just that single term. But then it's this last cross product that gets to be the hairiest, because we don't have that 0 in there to bail us out. And that's going to be this product minus this product. So it's 3 cosine s cosine t times 3 sine s cosine t. So that's 9 sine s cosine squared t. 9 sine s cosine squared t. And then minus negative 9, so plus 9, cosine s sine squared t. So if we were to find the magnitude of this vector, it would start to get real scary, and then a bunch of it simplify down using Pythagorean identity. But without taking the magnitude, there's really only one place where we have the ability to use a trig identity to make things simpler. If you notice, both of the terms written here in the z-coordinate have a common factor of 9 cosine s sine s, right? And if I factor that out, the cofactor is cosine squared t plus sine squared t, which by the Pythagorean identity gives us a 1. So I'm just going to kind of mark that in here like this, right? Those are going to combine together, and then that collapses this to just 9 sine s cosine s times 1 as my z-coordinate. But here's the thing. Here's one way that we can kind of make sense out of this awful looking parameterization. And that is that you notice it's not too terribly different from the original parameterization of the sphere that we had. What's the difference? Well, if I factor a common factor of 9 out of every one of my terms, and also a common factor of sine of s out of all of my terms, I'm going to bring those out to the front. So actually, no, let me factor just a 3 out. So 3 sine s. And if I do that, then what I end up getting, so that part goes away, we get a 3 here, we get a 3 there, and we get a 3 here. And I think I might have had a minus sign out of place. Yeah, I don't know where that little minus came from just now. That when I factor that term of 3 sine s out, what I end up getting here is just 3 sine of s times r of s and t. So what this is telling me is that a normal vector to the sphere is actually parallel to the vector that is the position vector of a point on the sphere. And another way to say that is, so what we find out is that the normal vectors to my sphere are just pointing just parallel to the vector that would join the point on the sphere to the origin, right? If I want to get a normal vector to my sphere, I just take my vector that connects my point to the origin and I just sort of keep going. I keep following it, right? And it gives me the normal direction to my sphere, which is exactly the same thing as we saw when we did this for circles in the xy plane. Right? And the reason, again, is this geometric idea that a tangent plane to a sphere is going to be perpendicular to a radius drawn from the point of tangency to the center of the sphere. So here are a collection of normal vectors with their magnitudes and directions having been determined by this formula that we came up with here, and their tails are placed at the corresponding point on the surface of the sphere. And if we did the same thing for the cylindrical and the planar parametrization, we would discover the same. Right? So the ultimate sort of the main point of this first activity is that taking the cross product of our parametrization's derivatives is how we can find a normal vector to a surface. And that normal vector can then be used, that's our next step, to come up with an idea of what the flux of a vector field through a surface ought to mean and whether that flux is positive or negative. So that's where we're going to go next, is we're going to do an activity that helps us to build that intuition. It's very similar to the two-dimensional versions that we've been doing up until this point, so this might go kind of quickly, I hope.